Hello, my name is Paul Steimer. I feel privileged to serve as the director of the Glasgow Computational Engineering Centre, GCEC, at the University of Glasgow. The vision of GCEC is becoming a world-leading computational engineering centre. Thus, since some 3 years, we pursue our mission to foster a community of people who learn, train, and work together on the discovery, implementation, and application of groundbreaking computational solutions to relevant engineering challenges. Making our vision to create a world-leading computational engineering center a reality is certainly a complex task, a challenge that we approach from the very beginning with utmost enthusiasm. To get going, we initially carefully designed our branding that you see in my background. Next, we continued with recruiting and onboarding our postdoctoral researchers and forming teams that among ourselves we denote as bubbles, vibrant thematic research units composed of postdoctoral researchers, lecturers, and senior lecturers collectively overseen by the senior members of GCEC. Based on this unique organization of the GCEC core team, we eventually started scientific work. Of course, at times the past developments were not without setbacks, that, however, we always overcame. Today, GCEC is flourishing, with already 4 bubbles pursuing exciting research, a great team spirit, its membership from within University of Glasgow growing, intra and extramural activities such as seminars and conference organization a routine, open source software providing high-end computational solution tools, and an ever-increasing involvement in collaborative proposals. We look forward to the years ahead, continuing to make GCEC a world-leading computational engineering center. Thank you. 2 of the PDRAs involved in the strategic support package will now give you some insight into their work and the GCEC community.
Hello everyone, I'm Zhaowei Liu, a postdoc research associate at the Glasgow Computational Engineering Centre. My research theme is geometrically exact formulations for strongly coupled problems. More specifically, I'm currently working to simulate and investigate the electromechanical coupling effects in thin structures made of active materials. I collaborate closely with our GCEC members, Professor Steinman, Professor Pierce, Dr. McBride, and Dr. Saxena. We begin by looking at the instabilities analysis of a toroidal membrane and made of electroelastic polymers. Snap-through winkling and loss of symmetry of the membrane during inflation was investigated. These instabilities can be used in the design and analysis of soft actuators. This work has been published in the world-leading journal, Journal of the Mechanics and Physics of Solids, JMPS. Following this more fundamental work, we aim to provide a finite element method for the simulation of electromechanical thin-walled structures. Thin structures are widely used in various engineering fields and are the focus of our current research. We choose to use the isogeometric finite element method with subdivision surfaces to solve high-order PDEs. We first assessed the IGA method using the scalar Laplace spectrometry problem and published our work in the journal Computational Mechanics. I was also invited to present this work as a keynote lecture in the IGA conference 2019. Then we extended this method to formulate a vibration analysis of piezoelectric shear. The numerical method was programmed using the open source FE package Tier 2. We collaborate on this with Luca Hitai in International School for Advanced Studies, Italy, and Yilin Xu in Xi'an Jiaotong University, China, in this project. This work will soon be submitted to a top journal. This project has allowed me to work on an exciting topic at the cutting edge of the science and engineering. I have used this opportunity to develop my network and present my research to an international audience. This will help me to develop as an independent researcher and establish myself as an academic.
In granular materials, it is common for many particles to move together in clusters. This can be seen, for example, in a simulation of a draining silo. These simulations keep track of the dynamics of each individual particle, but in situations like this, it is not an optimal use of the computer's resources. The project I'm working on aims to develop a simulation method for granular systems based on the quasi-continuum method. The key idea is to identify a series of representative particles with high density near regions where particles don't move in clusters and more dilute elsewhere. In dense regions, each particle is simulated as usual. However, in the low density regions, the deformations of the area between representative particles are simulated instead. Once these deformations are known, the other particle positions can be updated efficiently by applying the same deformation. This project offers many exciting opportunities to apply ideas from physics, computational mechanics, and granular flow modeling to problems that are common in many industries, from mining, pharmaceuticals, food processing, and geomechanics. The GCEC brings together the required expertise to make this project work, and so far we've developed an integration algorithm for granular materials that's compatible with the quasi-continuum method. A paper on the topic will be submitted in the upcoming weeks, and this work has also been presented recently at a workshop on geomechanics.
The next presentation comes from members of the broader GCEC community. Their work is funded by the EPSRC.
Hello, my name is Daniele Barbera and I'm a research associate at the University of Glasgow within the Glasgow Computational Engineering Centre. I'm responsible for material modeling and of course for the experimental work done in conjunction with our colleagues at the Advanced Forming Research Centre at the University of Strathclyde.
Hi, my name is Karol Lewandowski and my area of expertise is computational mechanics and software development of the open source library called MOFEM, developed at the GCEC. Together with Daniele, we are working on modeling of the incremental cold flow forming process.
Incremental cold flow forming is a relatively new manufacturing process which allows to form axial symmetrical component via the application of a uniform amount of force via a series of rollers. In the video that here is shown, provided by the EFRC, you can see the process in full details. In this case, two rollers are used to apply an enormous amount of pressure on a rotating thick sheet of stainless steel preform in order to form it into a cylindrical shape.
As you can see, this process can produce very detailed and complex geometries. However, material needs to be extremely plastically deformed to achieve the desired shape. Predicting the behavior of the material and the performance of a machine like this is critical to improve efficiency and lower the production costs. Existing commercial codes have proven to be unable to accurately and robustly model this process.
Numerically model such a manufacturing process is very challenging indeed. It requires several advances in different areas of computational mechanics. For example, it requires the ability to solve very large plastic deformation problems, but at the same time solving very complex quantum mechanics issues. And last but not least, the capability of predicting the amount of heat generated by the plastic deformation. All these cannot be achieved without a completely coupled computational framework.
Our research team formulated a new multi-field approach targeting all these challenges. Over the last couple of months, we have made a significant progress in our research. We are currently capable of running the first simple prototypes of cold flow forming simulations and can efficiently predict contact pressures and plastic deformation. This is just the beginning of this fascinating research project.
For me, it is an incredible opportunity to challenge all my capabilities in an exciting project which has the potential to impact the society. Of course, this work is not going only to impact the manufacturing sector, but the work that we are currently undertaking will be applied in unexpected areas of science and technology. For example, this numerical framework can be applied on biological nanoindentation or in the design of more complex and advanced aerospace components.
I find this project exciting because we will deliver an open source tool for manufacturing industries which use incremental cold flow forming. At the same time, we contribute into further development of our MOFEM library that was first initiated at the University of Glasgow. The success of this work will further show the importance of a dynamic open source software community like ours, which is building a platform for effective solving of the future challenges.
This work would not be possible without the constant support of our colleague at the Glasgow Computational Engineering Centre. We form a strong and unique community of researchers with experience in several areas, from computational mechanics, computer science, and also software engineering.
GCEC also provides us a great access to computational and laboratory facilities, which are constantly improving. The center is attracting world-leading scientists to numerous conferences, seminars, and meetings, even during the time of pandemic. I think that GCEC is a perfect place to become a world-changing researcher.
We are obviously disappointed you could not visit in person, but we hope this video gave you a sense of who we are in the center.